Hello, I am Dr. Subhojit from the Department of Chemistry, National Institute of Technology, Agartala. Today, I am going to talk about partition function, which is an important topic in the context of the course Statistical Thermodynamics. Partition function is a central mathematical concept insofar as statistical thermodynamics is concerned. It contains all of the essential information about a thermodynamic system under consideration. Through this lecture, I will attempt to provide an introductory background about statistical thermodynamics, discuss upon the concept of partition function, and finally look into the application of partition function in determining thermodynamic properties. At the end of this lecture, we shall see how most of the aggregate thermodynamic variables of a system, such as the total energy, free energy, entropy, pressure, etc., can be obtained from partition function or its derivatives. So what is statistical thermodynamics, also called as statistical mechanics? Statistical thermodynamics is a branch of science that connects or links classical thermodynamics with quantum mechanics. We know that quantum mechanics deals with ultimate particles of matter, including atoms, molecules, or subatomic particles such as electrons, protons, etc. Classical thermodynamics deals with large or macroscopic properties of matter. Thus, there is a gap between the two, quantum mechanics and classical thermodynamics. This gap is being bridged by statistical thermodynamics by way of doing statistical calculation on the behavior of microscopic particles and builds up the fundamental concepts about macroscopic systems. We can draw an analogy of this relationship of three branches of science with this example. Consider a jar of a gas and a balloon. The balloon cannot function the way it does unless the gas is filled in it. Quantum mechanics is like the gas and classical thermodynamics is like the balloon. What we need here is an inflator, a pump, to fill the gas in the balloon. Only when the balloon is blown to its full size. Thus the inflator acts as a link between the gas and the balloon. Statistical thermodynamics like the inflator acts as a link between classical thermodynamics and quantum mechanics. It is interesting to note that classical mechanics such as Newtonian mechanics, Hamiltonian mechanics, etc. developed before 19th century, while quantum mechanics developed after 19th century, about 100 years ago from now. The pioneers of quantum mechanics, namely Planck, Bohr, Einstein, they are being called as the founding fathers of quantum mechanics. They were being awarded Nobel Prizes for their groundbreaking works in the field. Interestingly, before the development of quantum mechanics as a subject, many of the statistical calculations were done by Maxwell, Boltzmann, Gibbs and others with the knowledge of classical mechanics only. Let us look at the difference between quantum mechanics and statistical mechanics. There is a clear-cut demarcation between the two branches of science. Quantum mechanics deals exclusively with atomic and subatomic particles of matter, such as it studies the position, the momentum, the energies of the particles. On the other hand, statistical mechanics only uses the information provided by quantum mechanics and does statistical calculation and builds up the concepts relating to the macroscopic properties of matter. The greatest gift of statistical mechanics to mankind is in the form of three statistics, namely Maxwell-Boltzmann statistics, Bose-Einstein statistics, Fermi-Dirac statistics, which are important for dealing with collection of molecules in gas phase of photons, phonons, electrons, protons, and other particles. So what is the difference between classical thermodynamics and statistical thermodynamics? As we have seen before, that while classical thermodynamics deals with bulk properties of matter, it has some serious limitation, such as it cannot explain the value of a thermodynamic property, such as if a property such as pressure assumes a certain value, classical thermodynamics fails to explain the value of the pressure, or for that matter any other thermodynamic parameter. Further, it also cannot explain many thermodynamical relationships. Statistical thermodynamics, which uses the properties of matter at the microscopic level, can very well explain many of the physical properties of systems. It is applicable to any physical system in any state of matter. Before understanding the concept of partition function, let us first of all understand the concept of distribution of energy. For that, let us consider a closed system consisting of a very large number of identical and distinguishable particles. Suppose the number of particles be capital N. And suppose also that the total energy of all the n particles is equal to capital E. Now, the total energy E has to be distributed among all the n particles. At no point of time will the particles of a system, say in the gas phase, will have a fixed value of energy. This is because we know that particles of a gas undergo constant random motion, and therefore they undergo random collisions among themselves and also with the walls of the container. As a result, there will be constant and random fluctuations in the energies of the particles. Let us consider that E0, E1, E2 be the values of energies that the particles in the gas can assume. And suppose that the degeneracies of the energy levels are G0, G1, G2 and so on. Let us consider one particular distribution where n0 number of particles have energy E0, n1 particles have energy E1, n2 particles have energy E2. Then, if we add n0, n1, n2 and so on, we should always get capital N, the total number of particles that is present in the container. And if we take the product of the number of particles with the energy which they possess, that is n0 multiplied with E0, added to N1 multiplied to E1 added to N2 multiplied to E2, we will get the total energy E of the system. So the total energy E is always consistent with the distribution here. Then the probability that the system will be in a particular state I, Pi, will be proportional to the degeneracy Gi. Then this probability is also proportional to the degeneracy multiplied by an exponential factor, which is given by e to the power minus Ei divided by kt. E to the power minus Ei by kt can also be written as e to the power minus beta into Ei, where beta is called as the Boltzmann temperature. It is given by beta equal to 1 by kt, and e to the power minus beta Ei is the Boltzmann factor. Now this parameter is very important because it gives us the probability of for a system to exist in a particular state I. Now Boltzmann distribution law is given by this relation, where Ni divided by capital N equal to Gi e to the power minus Ei by kt divided by summation Gi e to the power minus Ei by kt. This is called as the Boltzmann distribution law. It gives us the fraction of the number of particles that are present at any energy level Ei at a given temperature of the system. Say for example, the temperature is T. Also from Boltzmann distribution one can find this relation between the number of particles and the energy, that is Ni related to energy Ei. And this relation is an exponential decay sort of a curve, where we can see that as the energy of the system decreases, the number of particles also increases. That means that higher number of particles will be at a given temperature found at the lower energy levels, whereas lower number of particles will be found at the higher energy levels at the temperature of a system. Now the denominator in the Boltzmann distribution law, which is the summation of Gi multiplied by e to the power minus Ei by kt, is denoted by this letter q, little q, and this q is called as the molecular partition function. Why it is called so? Because it relates to partition function of a single molecule. How it is useful? Let us look at it. If we expand this summation, we will find that it gives us different terms, and each term relates to the energies and the degeneracies of the various energy levels, such as the first term relates to the lowest energy level having energy E0 and degeneracy G0, considering that the energy levels are degenerate in nature. So first term relates to the lowest energy level, second term in the summation gives us the contribution from the first excited state energy level, that is E1, third term relates to the E2 energy level, and so on. So considering that the lowest energy is 0, we will have first term as G0, and second term, third term will be as such. If the energy levels are G1 will be 1, G2 will be 1, and for the other energy levels also the degeneracies will be 1 each. So thus, whether or not Q will assume a higher value or not will depend upon the contributions coming from all the terms after the first term. And if we will see this expression, we will find that we have e to the power minus numerator energy and denominator we have the temperature. So depending upon the value of E, the energy, and the temperature T, Q will have a certain of value coming from the contributions from each of these terms. So thus we see that Q is a function of temperature and Q is also a function of energy. So let us first of all look at the dependence of Q on temperature. Here we can see the relation between partition function Q and temperature T. If suppose the temperature goes to absolute 0 Kelvin, then what will happen? Then most of the molecules will occupy the lowest energy level, and so other energy levels will be empty. So there will be no contributions from the energy levels other than the ground state energy level. So if we will look at this summation, we will only have Q as equal to G0, other terms will become 0, 0 each. So Q will be equal to degeneracy of the ground state or the lowest state for T going to or T tending to absolute 0. So as temperature will rise, the populations of the energy levels, various energy levels will slowly increase, because then thermal energy will increase of the molecules, and so as T will tend to infinity, most of the energy levels will be populated, and so we will get contributions from most of the terms after the first term, and so Q will assume very large value. And thus we have here that as T will tend to infinity, most of the terms will contribute to the value of partition function, and so the value of Q will be very large and it can be treated as infinite. Thus we can say that the partition function Q corresponds to the number of states that are thermally accessible to a molecule at the temperature of the system. Let us now look at the dependence of Q on the energy. Now, depending upon different types of motions that molecules can undergo, we have different energies, such as translational energy, rotational energy, vibrational energy, electronic energy, among other types of energies. And each of these energy expressions one gets from quantum mechanics. Now, since the translational energy levels are very closely spaced, the energy levels may be treated as continuum. And so, at a given temperature, most of the energy levels will be populated. And so, most of the terms after the first term will contribute to the value of partition function, and so partition function Q will be very large. On the other extreme, since the electronic energy levels are very widely spaced, at a given temperature, molecules will be at the lowest electronic energy level. And so, only the first term will be significant, rest of the terms will become 0. So therefore Q will be equal to G0 for degenerate energy levels, and for non-degenerate electronic energy levels Q will be equal to 1. Likewise, vibrational energy levels, which are smaller compared to electronic energy levels, will have some contribution from the terms after the first term, and for rotational energy levels also, because the energy levels are further smaller than the vibrational energy levels, contributions from any of the terms after the first term will be significant, and so Q will become larger. So if we compare the partition functions corresponding to translational energy, rotational energy, vibrational energy, and electronic energy, the order is like this, that translational partition function is highest compared to rotational partition function, which is greater compared to vibrational partition function, which is larger compared to electronic partition function. In fact, the value of translational partition function tends to attain values of the order of 10 to the power 28 to 10 to the power 30. The electronic partition function is mostly equal to 1, whereas rotational and vibrational partition functions assume values between 1 to 100. Partition function, by the way, is a dimensionless quantity. It is a pure number. It is interesting to note that while the various energies follow this order, such as electronic energy is the highest compared to vibrational energy, which is greater compared to rotational energy, and which is greater compared to translational energy, partition function follows the reverse order. Let us see how one can determine the molecular partition function Q. For that, we consider a simplest molecule, which is a diatomic molecule. We know that a diatomic molecule can undergo translational motion, rotational motion, vibrational motion, and also, of course, electronic transition is possible. So considering that the various energies corresponding to each type of motion are non-interacting in nature, and they are additive, so we can safely add translational energy, rotational energy, vibrational energy, electronic energies to get the total energy EI for the diatomic molecule. So what will be the partition function Q for the diatomic molecule? It will be equal to summation e to the power minus EI divided by KT. This sum can be expanded by replacing EI by the sum ET, ER, EV, EE. So what we will have? We will have product of the various exponential factors inside the summation. So this summation, each of these summations corresponding to partition functions corresponding to the translational energy for the rotational energy, vibrational energy, and electronic energy. So thus Q will become equal to a product of the individual partition functions. So what is important here is to note that while the total energy of a molecule is the sum of the various energies, the total partition function is the product of the various partition functions. One can find out the expressions for translational partition function, rotational partition, vibrational partition, electronic partition function, and these partition functions will be coming out to on solving each of the systems as shown on the right hand side. Let us look at an example to understand more as to what information does partition function Q provide to us. So let us consider the configurations that polymers can assume. So suppose say we have four different monomers connected to each other to form a polymeric chain. Now these monomers in the polymer chain can orient themselves as shown here. Four possible orientations have been shown here. Now if we consider the interaction between this monomer and this monomer, interaction will be the maximum here because of the close proximity of the two monomeric units here in this configuration, and there will be no such interaction between such units in the other configurations. So let us consider that for the molecular state I, the energy EI for the first one is, because there is interaction, the energy of interaction is suppose minus E of INT, energy of interaction. Since there is no interaction in the other configurations, the energies are 0. So we can say that the degeneracy is 1 for the first case. For the other cases, degeneracy can be treated as equal to 3. So if we solve the partition function for this polymeric configuration, we will see that it becomes equal to summation e to the power minus EI config divided by KT, the usual expression for partition function, and this sum can be expanded to include the contribution from the first and the other three configurations. So what we will have, e to the power minus of minus energy is plus divided by KT, plus 3 is the degeneracy multiplied by the exponential term which has 0 in the numerator because the energies are 0. So we will have this as the value of partition function for the configuration. Okay, so far we have talked about the partition function relating to a single molecule called as molecular partition function. Now molecules in a gas can and do interact with each other. So when we deal with a large assembly of molecules, we will have to take into account the partition function of all collection of all the molecules together. And this partition function for the collection of particles is denoted by capital Q, and it is called as the canonical partition function or the system partition function. So this capital Q can be found out once we know what are the partition functions of each of the molecules. We shall see how capital Q is related to small q, but before that we will have, let's see how the expression of Q is like small q, like we have the expression for small q, which is like small q equal to summation e to the power minus EI by KT, where EI stands for the energy of the molecule. Capital Q is equal to summation e to the power minus capital EI divided by KT. Here capital EI stands for the energy of a collection of molecules which are at a particular state I. Okay. Now this capital Q is related to small q in two different ways. For suppose say for distinguishable molecules means if we take the case of a crystal, all the molecules or the atoms in a crystal are localized in their positions, so they are distinguishable from each other. And if we know the partition function of each of them, then taking the product of the partition functions of each of these molecules will give us, if there are n number of molecules in the crystal, capital Q will be equal to small q to the power n. So this is the relation between canonical partition function and the molecular partition function. However, when we'll deal with gas molecules, we have to do one correction. That is, we cannot simply write capital Q as equal to small q to the power n for gas molecules. Why? Because energies of the molecules constantly exchange with each other. And so, at no given point of time, we can say that this molecule has this energy and that molecule has that much amount of energy. Because this is a dynamical process and the exchange of energy will be spontaneous. So we have to divide by the factor and factorial this q to the power n. Then only we get this canonical partition function for gas molecules. Lastly, I will conclude by showing some of the important relations which can be derived from this canonical partition function Q. In fact, all of the thermodynamic properties of a system can be expressed in terms of the partition function Q. For example, if we take internal energy U, it is equal to kT square d ln q dt at a fixed volume at a fixed number of particles and fixed volume. That means differentiation of log q with respect to temperature gives us internal energy U. What is the meaning? Meaning is that while capital Q relates to the behavior of atoms and molecules, so this information is provided by capital Q, and if one will differentiate log of capital Q with respect to temperature, one will get internal energy. Similarly, entropy has this expression: Helmholtz free energy, enthalpy, heat capacity, Gibbs free energy, and like that. In fact, we can find for any thermodynamic property a relation in terms of the partition function Q. Thus, partition function acts as a storehouse of information pertaining to the behavior of atomic, subatomic particles. And this information can be used to build up overall thermodynamical property of a system. With this, I will conclude this lecture. Thank you.